Okay, let's work this problem here. This is number 8 from fall 2011. The first question on Handic homework number 4. Wow. And so first step is to find the critical points inside. This isn't going anywhere. And then the second is to, on the boundary, do it as a Lagrange problem on the boundary. So take your x partial, take your y partial. Your x partial is 1 plus 2y. Your y partial is negative 2 plus 2x. They both have to be equal to 0 at the same time. So you set them both equal to 0. And what you end up getting, I believe, is the center of that circle. The x value is 1, and the y value is negative a half, I'm sorry. So you get the center of the circle. Y is negative a half, and x is positive 1. Okay, so it's a possibility. It's a candidate. It's inside the region. It's the less than. It solves the less than part inside the circle. And now we go for the boundary of the circle. And so we treat the equals to as the g function, the constraint function. So we want to find the max and min of f with g being equal to the equation here with equals, and also set equal to 0. You know, we have x minus 1 quantity squared, y plus a half quantity squared, minus 2. That's your g function. And your f function is x minus 2y plus 2xy. And you want to maximize f with the constraint g. The algebra comes out very strange with this problem. But it will work out though. Let's see. I have a picture of it. Somebody came by on Friday. And I took a picture of the board. Let me use that picture and then explain it through the picture. I'll just put it up here. Let me email it to myself. In the interest of time, and it'll be up here. It'll be on the recording. I can even send this whole picture file to you too. In fact, I'll do that. Math 114, 601, 12C. Yeah, I'll send it to the class. So I don't know how long it takes, but should be immediate. If you have the ability to pull up your email now, you can see it right in front of you. We'll project it here. 35 unanswered emails. That's ridiculous. No? Not immediate? Okay. In time, it'll come. Sending. Okay. Let's start it out at least, though. Let's set up our I don't know why. You don't have to do this way. I like the capital F function, though. So got this capital F, which is F minus lambda G. Okay, f minus lambda g, the capital F. And you have to take partials, partial respect to x, the partial respect to y, and the partial respect to lambda just as the constraint. And it's trying to solve where the partial with respect to x and y are equal to 0 is tough. I think you end up with solving for lambda in both as a technique that'll work. Let me show you this picture here. I just sent it to you guys too, so you should have it. I'll zoom in and I'll explain the different parts of it. It'll save us some time. Can I zoom in? Yeah. So can I drag? Dim the lights. Okay. Can I drag? Okay. So so we got this guy, and we take the x partial, write the same 1 plus 2y, and then maybe not zoom in so much. Is there any in between? Let's do this. Let's download. Okay, that's a little better. So anyway, we take an x partial. We get 1 plus 2y the same, and then minus 2 times quantity x minus 1 lambda. Take a y partial, same, but minus 2 times quantity y plus a half times lambda. We said both of these equal to 0, and the best attack is to solve for lambda in each. You should have this in your email now. At some point it should show up. So when we solve for lambda in the first one, just take this chunk and divide by it. Just take this chunk and divide by it. These two should be equal to each other. This is the approach that seems to work the best. Now, setting them equal to each other, though, ends up here. And I took out a 2 here. They both have 2. So I took out a 2, and we ended up here. And then cross multiply. Anyway, in all these, you don't have to always solve for, I mean, your goal is to get x as a function of y or y as a function of x. But even better than that, though, if you can get, like, if you go to the constraint and you see that there's just not an x, but maybe just an x squared, here it's x minus 1 quantity squared. If you could solve for that in terms of y, then that's enough. Take that and replace the x minus 1 quantity squared in your constraint with exactly that formula on y. And so we do that. We replace the x minus 1 quantity squared in our constraint. That's up here, I think. Yeah. X minus 1 quantity squared plus y plus a half quantity squared should be equal to 2, so that we're on the circle. And something nice happens in all of this. You know you're doing it right when you follow that through, factor out the y plus a half, and you end up with an equation that you can factor. You get two different y values. Y is negative 3/2 and y is 1/2. So that's on the circle, satisfying fx equals 0 and fy equals 0. And we then go and get what the x is that's associated with that. It actually turns out is 4 different points. When y is a half, we get x is either 0 or 2. How do we get that? Back to constraint. if you're in the circle and y is a half, then you plug in and you'll get two different x values. If you're on the circle and y is -3/2, you'll get the same two different x values. So it turns out that actually there's 4 points inside, 4 points on the circle. For a grand total of 5 points, you have the 4 points that are on the circle, and then the center, which was the critical point on the inside. And your job at this point is to make a chart evaluating the function f at these 5 different points. 4 of them are on the circle, and that we got from Lagrange. One is inside the circle as the critical number inside the circle. The function, with Lagrange, you're only going to get 2 values. You know you've done it right when that happens too. If you're doing Lagrange and you get 3 or 4 different values, something's not right. Lagrange should give you only 2 values or 1 value. Lagrange has given us 2 values, 3 at 2 of the points, -1 at the other 2 points, and then the critical number inside is giving us a 1. So the moral of the story is, you're doing this problem, it had a boundary, but it also had an interior to that boundary. You check the critical points in the interior, and on the boundary you might have to do Lagrange. When the boundary is nice and made up of lines, you don't have to do Lagrange, but when it's a circular or any kind of curve, chances are you're going to have to do Lagrange on the boundary, and that's what we went through. And so the maximum would be 3, the minimum would be -1, and the question actually asks for you to find the product of the maximum and minimum values of the function. So take the 3 and the -1, multiply them, you'll get a -3. The answer should be D. Okay, I just took the whole class that picture. I don't mind, I don't care, as long as you understand it. Yeah.
How does the way we approach the problem change with regard to constraint? Because it's written as less than or equal to 2, but what's written as greater than or equal to 2? Is there a difference in the way?
It's a different region. That's the exterior of the circle.
And when we form G of x, y,
the region needs to be bounded. See the extreme value theorem that we said back in 14.7? The region needs to be closed and bounded for us to ensure that we can find an absolute max and min. Sorry about this. I don't know why it's scrolling like this. So if you're talking about greater than, that region isn't bounded. If you're talking about greater than a circle, you're talking about the exterior to a circle, and that goes on forever, both in x and y. That's an unbounded region. We can't answer that question with a surety. But when we're talking about a bounded region, so the question will be either interior or on. It won't be greater than, because normally that'll be a unbounded question. And for the extreme value theorem, we need for it to be bounded and closed, for us to say for sure that it will obtain an absolute max and absolute min. Yeah. So that's number 8, this first question there. It's a hidden Lagrange problem. I think if I was to ask it, it would just be Lagrange. It would just be equals to, if I was to ask it on an exam. I think the extra step of the less than just confused things when, the heart of that whole question was us digging through the Lagrange multiplier method. Okay, so hopefully that was worthwhile. I don't know. It's just it's the algebra got tough there, but yeah, that's how it works. That's how that question is supposed to be solved. Okay. More questions, please. Yeah. This one here, spring 2011, number 7. Another Lagrange. This time you have a z. We haven't seen one of these yet. Well, what do you think? It's just going to be an extra variable, an extra derivative to take, an extra derivative to set equal to 0, and instead of being 2-dimensional, our region is 3-dimensional. It's a sphere. And so I have this function where I multiply x and y, multiply y and z, add them together. I want to find the biggest that could possibly be on the sphere. So this is just straight Lagrange only, no less than. And the sphere is going to make up your G equation. And the F is your maximize, minimize equation. Sometimes, though, Lagrange only comes up with one answer. Now, most times we've seen that Lagrange giving us two different answers, but if it's one answer, we just have to make an argument as to why that is the, the maximum. And so, yeah, let's work this out. At least get it started. If you came in late, what we're going to do as a compromise, not move the exam. Exam's still going to be on Monday. But take off the new material that we did last time we had class. A week ago today we had 15.2 and 3. Also 15.1, but 15.1 is something that you could pick up quickly. And so we'll just take that off and put it on the next exam as a compromise. What we missed on Monday would have been us going through that thoroughly so that you understood it well enough for the exam. So instead of us pressing forward and still having that on the exam, we'll just push it to next exam. This material started with 13.5, tangential and normal components of acceleration, the torsion. And then we went through all of multivariable, chapter 14, derivatives, all the way up through Lagrange and 14.8. And then we'll put 15.1 on it as well. Before you guys came, the ones who came late, I basically updated our exams page. I updated our exams page to include this practice exam. The problem with it is that it's off. Like basically, there's only 4 questions that are useful to you on it. The first one isn't, and the last 2 aren't. Now that we move stuff away, we'll put these back on. We'll do these. And this first one we already did on our last exam, and so really it's only questions 2 through 5 that are useful. But there's a Lagrange question there, and there's a classify max-min question, max rate of change question, tangent plane question. So standard, but only 4 of them though. So try that. So homework 3 is due today, as you've been doing. Just come and turn it in as you come in. We have a grader now that's going to grade them and get them back to you in a timely manner. Homework 4 is due on Monday. Most of these questions that people are asking are from homework 4. And then there's also an online homework that's due on Monday. It's just labeled 14.5 through 14.8. That's what it's labeled. And so there's no 15 on there. But we can pick up some 15.1 questions if you want. So that's where we're at as far as announcements. And before you came, the only thing we did was work through this problem, the first one on the homework 4. And what I did was I had done it in my office with a student on Friday. And so I just emailed the class this picture of the board, which works through all the algebra. And I talked through it. And that's basically what you missed if you came in late. So now we're going to move on to the next question. Which is number 7. We'll take it as far as maybe just setting it up. And maybe the technique of solving for lambda will work on this one too. I don't know. I would try that as a technique first, pretty much as a standard. See if that'll work first. Solve for lambda in each, if possible, if it's reasonable, and set them equal to each other. Just remember, all the while, your goal is to get some relationship between x and y. In this case, now x, y, and z. And it doesn't have to be like x equals some function. It could be, x squared equals something on y, and z squared equals something on y. So you can actually go and replace the whole x squared and the whole z squared. So let's see how far we can take this. Let's go ahead and set it up as capital F is the little f. There's a delay here. I'm sorry. Because I'm recording, there's a delay here, but it'll show up in a second. Minus lambda times g. Now g is the constraint, remember, but set equal to 0. So x squared plus y squared plus z squared minus 4. And we take the x partial and the y partial like we've been doing. Let's also take the z partial now. So f sub x is going to be y plus z. No, I'm sorry, just y. What am I doing here? Sorry. F sub x is just y, and then the lambda part. Sorry about that. F sub x is y minus 2x lambda. Sorry about that. I'm supposed to turn it off. Forgot to turn it off. Okay. And f sub y is x plus z minus 2y lambda I don't know what that is. It's supposed to be, okay. Then f sub z is y minus 2z lambda and we have to set each of these equal to 0. So on the one hand, lambda is equal to y over 2x. On the other hand, lambda is equal to x plus z over 2y. Sorry about that. They ran together. I couldn't see where it was writing that. And on the other hand, lambda is equal to y over 2z. So you see how the first and the second are kind of, the first and the third are kind of symmetric. Basically, you can almost immediately conclude from that the x has to be equal to the z, pretty much, right? Y over 2x has to be y over 2z. Taking these two together, we get y over 2x has to be y over 2z. So yeah, x is z. Okay. Taking that then into the second one, knowing that x is z, that numerator, which is supposed to be x plus z, is now just 2x. So it says, let's go back and maybe combine, let's combine 1 and 2 together. So this is from, if I call this 1, this 2, and this 3, this is taking 1 and 3 together. Now let's take 1 and 2 together. And now that gives us the relationship between y and x. And then we're on our way. From 1 and 2 together, we get that y over 2x is 2x over 2y, knowing that z is x. So 4x squared is 2y squared. You don't have to solve for y. You can solve for x squared. That works great. So x squared, maybe y squared is, yeah, let's go y squared is 2. I don't want to do fractions. So let's go y squared is 2x squared. Is that okay? Your goal is to get either all x's, all y's, or all z's. And I'm going to get all x's. I know that y squared is 2x squared. I know that z squared is x squared. So I can use these as the facts I was searching for. I was searching for facts that relate my variables to each other. So now I take this information into my constraint, which is x squared plus y squared plus z squared. So when it comes time to take the y squared, I'll replace it with 2x squared. When it comes time to take the z squared, I just replace it with x squared. And it should be equal to, what's the circle here? What's the sphere? 4? Equal to 4. Is that the sphere? Yeah. X squared plus y squared plus z squared should be equal to 4. So I take these guys and I'm on my way now. I'll let you finish it out from here. But in the constraint, if I want to do f lambda, I could. I'll just go right to the constraint that x squared plus y squared plus z squared should be 4. And now replace these guys. And you'll see it's convenient. It works out numerically well. I try to pick problems that work out numerically well, at least for the exam. Some of the ones that are on my math lab, there's some roots involved, and sometimes it gets a little messy. But this is manageable here. What you end up with is x squared, and then 2x squared, and then another x squared should be equal to 4. So that works out great numerically, so that we get 4x squared. We get an x squared, a 2x squared, and an x squared should be equal to 4. So 4x squared should be equal to 4. So x squared is 1. Plus or minus. Okay, this is a Lagrange multiplier question. We have to find the maximum value of the function subject to the constraint. And I'll let you finish it out from there. The hard work has been done, though, by you digging through the fact that all these partials need to be 0 at the same time. I'll let you finish it. I'll stop here. Yeah. It's like a W function. W is equals some function of x, y, and z. So yeah, you got to get the x, y, and the z. It'll be a 3D coordinate, and it should be more than one. You go and basically plug them in. One will give you one value, the other will give you another value. The biggest is the maximum, and they want that maximum there. Yeah. So it's really minor to finish this off. We've done the legwork. We've done the hard work. Okay. The hard part is digging through the Lagrange, and this technique seems to be working for us. It won't always work. I would say, it's good that it's worked in our last 2 examples. Solve for lambda in each. Set them equal. Seems to work. Yeah. Let's get rid of some of this bloat. Okay. If I could find my mouse. Oh, there we are. All right, get rid of some of this junk here. All right, give me that one more time. Spring 2010.
Yeah, no problem.
Yeah, hear it again. Less than or equal to. Okay. This time we can immediately say that there will be no interior points that are critical points. Look at those partials. There's no way that that they're going to be equal to 0 all at the same time. So step 1 is to find the critical points inside, but there will be none. That takes care of the less than. Okay. But immediately, when we go take our partials, fx is 2, Fy is 3. Fz is negative 2. They'll never all be 0.
Why can you not find
A critical point is a place where all your partials are equal to 0. It just can't happen. Okay, now we Lagrange for the rest of it. Yeah, just like that other question. Had it been nice and rectangular, we wouldn't have to Lagrange. It'd be like the one in our notes. The one in our notes, we just rewrite the function, and it'll end up being a single variable function. It was so nice. But this one's not that. It's a curve. When your boundary is a curve, you got to Lagrange it to find the max and min on the curve. Okay, so we've taken care of the less than, saying there are no critical points inside. Although the first one had a nice critical point on the inside. It worked out so special that it was the center of that circle. The first one on homework 4. This one, no critical points inside. All right, fine. Now let's deal with the boundary and turn it into a Lagrange question. The boundary becomes a Lagrange question. The equals to part on the boundary is a Lagrange question when it's a curve. Okay. So that makes your G equal to 4x squared plus 6y squared plus 2z squared minus 18. This is some ellipsoid. Not a sphere, but an ellipse. That's your G. Remember, if you're doing Lagrange, you gotta have an F, you gotta have a G. The F is definitely defined for you. The F is definitely that function is up there labeled as lowercase f. We need a G. And then we set up our capital F, which is lowercase f minus lambda G. I'm sorry about the delay. Okay. Yeah. So we have x, fy, fz. This shouldn't be that bad though. This should be, with the f being so reasonable, it should be manageable. Let's try it out. With the little f being so reasonable as far as the partials on it, this should make this really doable. Let's see. F sub x is what? 2 minus 8 lambda x. Ooh. Okay. F sub y is 3 minus 12 lambda y. F sub z is negative 2 minus 4 lambda z. Okay. Set these all equal to 0. And let's do the solve for lambda approach. Technically, we have to be careful about what we're doing here, because when we do the solve for lambda approach, we're dividing by x and y and z. Just make sure they can't be 0. That's all. On the one hand, it says that lambda is 2 over 8x. On the other hand, it says that that lambda is 3 over 12y. On the other hand, it says that lambda is negative 2 over 4z. Okay, but yeah, we'll definitely see that, z can't be 0. Just based on this equation, these guys can't be 0. So it's fine for us to do that. If this guy was 0, we wouldn't have a true equation here. No matter what, if z was 0, then, if we weren't allowed to divide by z, if z was 0, this would, fz would not be true. This fz equation, the fy equation won't be true if y was allowed to be 0. The fx equation won't be true if x was allowed to be 0. So it's okay. You should consider it, but it doesn't make sense here to let those guys be 0. And so we set these equal to each other. And reduce, I didn't reduce, but we can. It says that 1 over 4x is the same as 1 over 4y. Well, that means that x is y. And this last one is negative 1 over 2z. So this is, if we call this guy 1 and this guy 2 and this guy 3, this is taking 1 and 2 together. Okay, see the process that we're doing? We gotta make sure we at least pair up enough to get the information we need. Now we take, let's take 1 and 3 together. It says that 1 over 4x is negative 1 over 2z. So what's that? That x is that z is twice x. Oh no, z is negative 2x. Z is negative 2x. Okay. All right, that's what we need. We needed some relation between x, y, and z. In the end, you want to have one of them in terms of the other two, the other two in terms of one of them. So I'll replace all my y's with x's. I'll replace all my z's with negative 2x in my constraint equation, and I have an equation only in x. And I can solve it. And I think, yeah, it'll be a nice integer answer. Okay. If x is y and z is negative 2x, I think it's meant to come up with 18 x squared. It's convenient. Okay. I'll let you finish this out. You get the point? Who asked this? Yeah, we're good? Okay, yeah, Mike.
When you're finding the x, y, and z values,
Yeah.
they're eventually going to plug in. So like, if you get 2 values for x, when you plug that into the y, you get like another 2 values.
Yeah.
And then let's say you plug it into the z equation, so you get another 2 values.
Yeah.
Do you then have, what is it, like 8 different points just for that one x value?
1x and I think it's 8 total. 1x gives you 4 and the other x gives you 4 combinations of y and z. The 4 ways to mix the y. So if x is 2,
Okay.
oh, x and y have to be equal. So it's not the case here. In some cases though, yeah, if you have something like that other one we had, y squared equals this. So if we know so it could be possible that when you get an x, you plug it in, you'll get 2 y's, and then but then you take that x, you plug it in, you get 2 z's. So then the 1x giving you 2 options for y and 2 options for z spawns 4 different points. The other x, if it's plus or minus or something, we've got to spawn another 4 points. It could be possible that you have 8 points.
Okay.
It's possible. But in the end, though, Lagrange should still only spit out 2 values. No matter how many points that falls out of Lagrange, only 2 function values should come out. And the biggest function value is the max, and the smallest function value is the min. Yeah.
Regardless, strength and reliable efficiency.
I just want to make sure we're okay with this one first. We're ready to move on. Spent a lot of time on Lagrange. The test is over. Lots of other stuff. Just want to keep that in mind. Okay. What is it now?
Strength and reliable efficiency.
We have to classify the critical points. This is a 14.7 question. Find and classify the critical points. And so it requires us to do the same kind of thing. We have to go and take the x partial, take the y partial, set them both equal to 0. But then we have to go and create this capital D function to get the kind of like a second derivative test that lets us know what these critical points are. Are they local min? Are they local max? Are they saddle? And so let me get you started on this one. So what's the x partial? (3x squared minus 6y). Yeah. How about the y partial? Negative 6x minus 6y. 6y? 6y. Okay, that's 3y squared, not 3y cubed. Be careful. Okay. Set them both equal to 0. And we have to figure out what that means. Okay. Factor out what you can. So in the first one, I just see I can factor out a 3. And it tells me that if I factor out a 3, what I get out is x squared minus 2y. Has to be 0. If I factor out a negative 6 on this one, it tells me that x plus y has to be 0. Both of these have to be true at the same time. These don't live in a vacuum. Like they both have to be true at the same time for you to have critical numbers. So on the one hand, x squared needs to be equal to 2y. On the other hand, x has to be the opposite of y. Take these facts together. Let's take the second equation, plug it into the first equation. Every place you see an x, put a negative y. It says that y squared has to be equal to 2y. Or that y squared minus 2y is 0. It gives us two values for y. It tells us that either y is 0 or y is 2. I do it this way so we don't forget the y is 0 option. If I just would have done the divide by, if I just would have, I don't know, there's an easy way to miss something there. Anyway, y is 2, y is 0. Quadratic, set it equal to 0 and try to factor it. And when there's no constant, it makes it nice for you. And x is the opposite of y. So we get that x is 0 and that x is negative 2. Two critical points. 0, 0, negative 2, 2. Okay, what do we do with these guys? We need to create a second derivative test, kind of, the analogous of it, and now in multivariable. It's called the capital D function, which takes into account all different forms of second derivative. Capital D, discriminant, I think it stands for, is the double x partial times the double y partial minus the mixed partial squared. And we have to evaluate D at each of the critical points. Okay? So we could do it in general and then plug in, or we could do it specifically for each one. Let's just get the second partials. What's f double x? That's it. Very good. And f double y? Doing great. And the mixed guy? Wonderful. Now if you plug these in general, just as they are, into this capital D function, what we get out is a negative 36x for this part. And from that we subtract 36 because we take negative 6 and square it, but then a minus. So it's actually a minus 36. Okay, that is capital D. And we have to evaluate capital D at each of these critical points. So the y ends up not mattering for capital D, only x matters. And so we have capital D at the origin is negative. The actual value is negative 36. We don't care. It's the fact that it's negative that we care about. We can immediately say that it's a saddle point. When capital D is negative, it's a saddle point. Okay. Now we have capital D at the point negative 2, 2. And that's a positive 72. Okay, when it's positive, we have to go further. When it's positive, we have to then go and check double x. Just by convention, it's double x that they use. It's not any more special than the other second partials, but that's what every book uses, so we'll use that. Which is a negative 12. Why do we care? It's going to tell us whether we have a local min or a local max. Capital D is positive, but f double x is negative. This combination, the way I keep it straight is I think about concave up and concave down. I treat my double x as telling me which one it is. If my double x is negative, then I have a concave down, like a frown, so I'm going to have a max. You do whatever you need to do, but it's a max. This combination means local max. Had it been positive, it would be concave up like a cup. And so, it's a local min. Anyway, we're done. So it answers the question. There is one local max and one saddle. Letter A. Yeah. You have another question? You ready to move on from this? Go back down. Go back up. Back down. Go over. Did I write something? I don't think I wrote anything. Yeah, we're good. Yeah, so if we have to do this, so it'll be a question like this. It'll be a Lagrange question. I don't even guarantee it yet. Good. Okay, Tanya, you're up.
Number 6 in my MATLAB.
Oh yeah, I forgot about those. Okay. Am I logged in? Oh, I was logged in. All right, I'm not logged in anymore. Hold on. Just give me 1 second. Number 6? Okay. Oh yeah, this question. All right, I'm sorry if yours has different numbers, but is this okay if we just do this one? Okay, I have this function, and I want to find the directions. It's weird. Usually we have the directions to start out with. Okay, fine. Find the directions u and the values of the directional derivative for which the following is true. A and B are straightforward. A, you know that your directional derivative is largest in the direction of the gradient. And so this will be the gradient of f. This guy will be the opposite of the gradient of f. They also want the value, though, and the value would be the magnitude. Okay, so anyway, what's f? F is this guy up here. It's hard, it's very small, I'm sorry. And the gradient of f is a vector that has partial derivatives as the components. The x component, the I component here, is the x partial, 2x minus y. The j component is the y partial, 2y minus, negative x plus 2y minus 1. Okay, that's the gradient on f. Directional derivative is going to be largest. There's a given point. I didn't see that. At 1, negative 1. Okay, so we take this guy and evaluate it when x is 1 and when y is negative 1. 3. Negative 4. Okay, not unit, but these guys need, u is meant to be unit. So, but we can easily turn it into unit when it's not unit by dividing by the magnitude. And what's nice is that the magnitude is a nice integer here, 5. 3, 4, 5. So the answer would be 3/5, negative 4/5. Okay, and the magnitude of the gradient is the actual value of the directional derivative, with the max value. The magnitude of the gradient is the max value of the directional derivative. It's the max value of the directional derivative. And so it's 5. It's 5. And it occurs in this direction. Okay. So that's A. And then B is just the opposite of that. So B is going to be negative 3/5 and positive 4/5 is the direction, and it'll be the opposite of the gradient, or negative the gradient, I guess. Negative the magnitude of the gradient. That's the min value of the directional derivative. So negative 5. Oh, sorry. That got pretty bad there. So negative 5. Okay, great. But then the real trouble comes in really D and E. C actually ends up okay. What you do for C, we no longer can use the gradient. We know that the biggest this guy gets is 5, and the smallest this guy gets is negative 5. So then they start asking us, what about numbers in between? How can I know the direction U so that I get the directional derivative to be 0? How can I know the direction U so I get the directional derivative to be 4? It becomes a system of equations that you have to set up. Basically, you have a generic U vector. I don't call it A and B. And so for C, at least, we can say that if you want this directional derivative to be equal to 0, remember it's a dot product. It's a dot product between your gradient vector and the unit vector. The unit vector didn't play a role in A and B. We ended up being that it was just a gradient vector. So what happens here though is just say that U is some A and B. We have to now chase down what A and B are. Okay, so it's the same gradient that we have from above. I don't think we need to. We can go with the non-unit version of it. We could take and do the 3, negative 4 version and dot it with AB. Now that only gives us one equation. This guy is supposed to be equal to 0. This dot product is supposed to be equal to 0. Dot product between these two vectors is supposed to be 0. But that only gives us one equation on A and B. It just tells us that 3A minus 4B is 0. Or that, that A is 4/3 of B. That's all it says. Okay. Or 3A is 4B. Okay. That's not enough. And we just take the hidden fact that U has to be a unit vector to get us the other relationship. A squared plus B squared has to be 1. So the other equation is that A squared plus B squared needs to be 1. Take these two facts together, you'll be able to chase down what A and B are. And then do it the same for if instead of 0 you have a 4, if instead of 0 you have a 3, or is it negative 3? Negative 3. So repeat this whole process, replacing 0 with 4 for part D, replacing 0 with negative 3 for part E. It'll be more difficult, but you can do it. 0 is nice because you can directly get this relationship and you can easily plug it in here. But with a 3 and a 4, it just doesn't, a negative 3 and a 4 for parts D and E, it just doesn't turn out so nice. You'll still be able to solve it though. Everything is repeated. It's just the algebra is harder. Yeah.
I don't understand the A squared plus B squared equals 1.
It's a unit vector. Unit means magnitude 1.
Okay.
I'm sorry. I should have said it. The unit vector here, this guy is unit. So its magnitude is 1. I'm sorry. I mean, there's another question over here. Hi.
Yeah, so what do we do after we set A squared, B squared equal to, we just like,
So there's two equations here. I'm sorry. I thought it. There's this equation,
then find like.
and there's this equation. You need to solve.
Okay.
I can do it if you want.
No.
This was nice because you can just say A is that and sub. You can do a substitution.
Okay, we just.
The other ones won't be so nice.
Like A equals concurrence of B, and we just like plug it in.
Yeah, it comes out. But the other one's not so nice. The 0 is very nice. Yeah? Yeah. Let me make sure we're done with this. You okay with the whole just finish the rest of it part? It won't be nice, but you can do it. Replace 0 with negative 3 for E. And replace 0 with 4 for part D. I don't think this is a randomized question. I think everybody has the same version of this question. And it's messy, but it's doable. Move on? Okay, move on. Go back to the homework you just handed in. That'd be homework 3. Okay. And what question? Yeah. This becomes a Calc 1 related rates problem. Okay. The initial equation there, the ellipsoid equation, it means nothing. Really, you start with that second equation, the volume equation. And the A, B, and C are all functions of time. A is changing with time, and B is changing with time, and C is changing with time. So we have to take a derivative of velocity, volume with time. When we go to do it, though, there's a chain rule that we have to take. And so what happens is it's a little easier than it looks. It gets it's deceptive because they throw that ellipsoid equation at you, and you're thinking you need to use that. But no, from it though, we just get the volume of the ellipsoid is this formula. You know, if it's a sphere, 4/3 pi r squared. But when it's ellipsoid, we just get that, which is nice. They gave that to us. We don't have to figure that out. Later, we'll be able to prove this. Later, when we do integration, multivariable, we'll be able to prove that this is true, that the volume is that. But for now, we'll just go with that and start with that equation, that the volume is 4/3 pi times ABC. And then the A, B, and C are all functions of time. So that when we go to take the time derivative, we have to consider the chain rule. I want the time derivative of I keep wanting to say velocity, I'm sorry. I want the time derivative of volume. I want dv dt. And so this constant, just carry it. 4 pi over 3, just carry it. It won't end up playing a role. And I need to take the derivative of this ABC. First starting with A, so I get BC. But A is a function of time, so chain rule says don't stop there. The derivative isn't just BC. The derivative involves the derivative of A with respect to time, which we know. I think we're given that value. Then move on to B. B, the derivative with respect to B is AC. But don't stop there. Chain rule says no, B is a function of time, so you multiply by dB dt. And so on. I'll let you finish it out from there. You know 5 of these. You just need the 6th one. Why? Wait. Well, what is this? So the volume needs to remain constant. If something is remaining constant, its derivative is 0. And you're on your way. I'll let you finish it off. Yeah.
I just don't really understand what you're adding.
It's a chain rule. When you do the chain rule, you add the different parts together. You don't multiply. And yeah, I can pull it up. The notes from 14.3. Yeah, or 14.5, 4. Jeez, I don't know what section it is. I'm sorry. Put it up. It's dv dt is the it is the partial of v with respect to a times dA dt. But don't stop there. Do it for the other variables as well. And then the other guy. This is the single variable chain rule. When your input variables are single variable functions. The multivariable, when your inputs are multivariable, then there'll be those d's will turn into partials. So yeah, that's how it works. However many variables v has in it, you just keep going to that many parts, keep adding one. Yeah. More questions?
On this same homework, fall 2010 7.
Okay. What is this code word for? The vector pointing in the direction of fastest increase. Is the gradient. Okay? So we need the gradient of f. Gradient of f. Okay. Just refusing to put the gradient symbol. Alright, so okay, there's a lot of them. Alright, so here we go. What's the x partial? Beautiful. What's the y partial?
Negative 2xy.
And the z partial. That's great, that's the gradient. At that particular point though, 0, -2, 1. Yeah? Alright, here's the hard part. And the x, what do you mean, the x-axis? Okay, that's an axis, that's not a vector. I can talk about angles between vectors. I don't know about this vector and this axis. Okay, so how can I turn axis into vector? Because I can do angle between two vectors. Okay, so what's a vector that points in the direction of the x-axis? That I can use that. Any vector I want. Any vector that points in the direction of the x-axis is usable to me. Do you have one in particular? This needs to be a vector. So we get a vector. Any vector that points in the direction of the x-axis. Both y and z have to be 0. But the x can be anything you want it to be. 1's nice. Doesn't matter. As long as it points in the direction of the x-axis, you're good. Doesn't matter how long it is. Just as long as it points in that direction. Alright, so we're good. Let's go 1, 0, 0. Let's use I. There you go. Angle between these two vectors. Using the cosine theta formula. I'll let you work it out. It works out nice. It doesn't matter because it also doesn't matter because the x here is 0 when you go to dot them. It does, whatever you put there won't matter because, and then these other two guys are 0. The dot product is 0.
Okay.
So it's 90 degrees. Done. You could also analyze it saying that this guy is in the YZ plane and this guy is in opposite to that. It's parallel to that. So perpendicular to that. Yeah, these guys are perpendicular. Angle's pi over 2. Yeah.
So we didn't have to find the magnitude of the gradient and then like divide it at all.
If they want to know the largest value or the fastest increase value,
Okay.
then magnitude of the gradient.
Okay, so even if we like scaled it by.
You still get the same answer if you scale it.
Okay.
It's not about the lengths of these vectors. You know, if I want to know the angle between two vectors, I don't care how long they are, I'm still going to get the same angle. So if you do scale it, you'll still get it right.
Right.
But don't make a unit if you don't have to.
Okay. Cool.
Yeah.
You do a maximum rate of change problem?
Maximum rate of change. Yeah. Everyone. It's just code word for gradient. Maximum rate of change is code word for gradient. So, like in this practice exam thing that I give you, maximum rate of change, code word for gradient. So find the gradient. Might be a bit messy, but you can do it. Plug in those points. Plug in those coordinates. X equals 0, y equals 0, z equals 1. And yeah, that'll be your answer. The magnitude of that. Maximum rate of change is the magnitude of that gradient. Here they want the magnitude.
Okay.
They don't care about the direction in which it occurs. They're not asking for that. So code word for maximum rate of change is magnitude of gradient. I'm sorry, I misspoke when I said gradient. Those are some nasty derivatives there. And number 4. 2 is standard. That's a standard kind of question. Tangent plane question. 3 is, yeah. 4, it's going to be messy. And 5 is a Lagrange. It won't be easy there. Yep. Anyway, more questions. Basically, if I give you a limit question, it'll be ahead of time that you'll know that the limit exists. This has a mixture of 1 where the limit exists and 2 where it doesn't exist. So you'll know ahead of time, how to attack the problem. I'll tell you, this limit exists, go find it. In Roman numeral 1 or I here, this limit exists. To find where a limit exists or the value of a limit when it does exist, you have to use algebra basically. There's no like Lagrange. Yes, if you plug in 0 and 0, you do get 0 over 0. But there's no L'Hopital's rule kind of thing where you could take the derivative of the top, take the derivative of the bottom, and then try again. Because it's more than just one derivative, and so to get these limits that when they do exist, we have to fall back on 2 things. One which we will never do anyway, the definition of the limit, epsilon delta definition, or somehow algebra to help us out. And in Roman numeral 1, there's algebra to help us out. Back when you first learned limits, back before your very first semester of calculus, your very first experience with calculus was finding limits. You had to use algebra to find the limits. You didn't know what a derivative was. You didn't know L'Hopital's rule, so you had to use algebra to help you out. Factoring, multiplying by the conjugate, clearing out the fractions, and so if you factor the numerator as difference of squares, you'll be able to cancel out the denominator in Roman numeral 1. Otherwise, though, when you're told that the limit doesn't exist, basically I want you to go through the 6 different paths. So for this first one here, we can just say factor as the difference of squares x squared minus y squared x squared plus y squared. So you can cancel. As soon as you take care of the issue of division by 0, you can immediately plug in the values of x and y. There's nothing to stop you. Before, we were blocked. We couldn't plug in the origin, but now we can. So we get 0. For more practice with this, you should try the problems that are in section 14.2. There's sets of problems where they say, here's a limit, go find it, or this thing has a limit, go find it. And then there's a set of problems that say, these don't have a limit. The limits don't exist here, and explain why. And so that's what these two are. These two are, the limits don't exist. You don't know ahead of time. I mean, there's no algebra that you can do to solve it. I mean, to simplify it. I can't cancel my issue of division by 0 in Roman numeral 2 and 3. That's a hint that maybe they don't exist. So you have to try one of our 6 paths. Six paths. They are x equals 0, y equals 0, y equals x, and y is the opposite of x. Y equals x squared, and occasionally you'll see that all of these work to give you the same limit, but this other guy here, the last guy, x equals y squared. Whoa. Sorry about that. X equals y squared. So you know, technically there's infinitely many paths. What I'm telling you is that try these 6, you know, and you should get some disagreement. As soon as you get disagreement, then that's it. The limit doesn't exist. So yeah, that's what'll happen with these. If for Roman numeral 3, if you go along the line x equals 0, you get a 1. But if you go along the line y equals x, you get 1 over root 2, something like that. Whatever, it's not 1. For 2, x equals 0 gives you negative infinity, y equals 0 gives you infinity. I think they disagree. So that's enough to show one disagreement from the 6 paths. I'll make sure that it'll disagree on one of these 6 paths. You'll know ahead of time. You shouldn't have to guess. These won't be combined into one problem. If I give you a limit problem, I'll tell you that this limit exists. Go find it. Use algebra to simplify it, to cancel out your issue of division by 0. Otherwise, I'll tell you that the limit does not exist, and just explain why by trying one of these, a pair of these 6 paths that disagree. Yeah.
What should we know about like torsion and acceleration?
Torsion acceleration, 13.5. Yeah. Yeah, it's going to be on it. That's the first section of new material. Is the oldest material that we had. But yeah, there's notes up for that. All right, am I just saying that, or is that true? Yeah, notes are up for that. 13.5? Yeah, 13.5 is where we start at. Tangential component acceleration, normal component acceleration. There's formulas. I basically say just go with not these formulas, but these guys here. These are the ones you use most of the time. If for some reason I give you curvature, you know, I mean, it's too much of a hassle to go find curvature. But if you happen to know curvature, you can use this formula, but it's not necessary. And then here's a question that worked out, an example of that worked out for something that's not so nice, but it works out. And then, yeah. And then torsion. The formula here, how you go and find it. There's a numerator, there's a denominator. The numerator is pretty involved. It's a scalar triple product. It's a dot and a cross. So you just take velocity, acceleration, and the third derivative, which is called jerk, throw them into a matrix and find the determinant of that. That's your numerator. Your denominator is the cross product between velocity and acceleration. It's magnitude squared. And so here's a calculation here of an easy one, and then a much more difficult one. But it turns out to let you know that the point is that it doesn't always give you a constant. This one is a nice constant. Torsion is constant. Torsion is the degree of twisting that a curve has. The helix has a constant degree of twisting, if you think about it, as it wraps around and goes up, or I guess in this case, goes along the y-axis. But this function here, I don't think it has a name, but anyway, this particular vector curve here doesn't have a constant torsion. As torsion, as the time t starts at 0, the torsion is undefined. And then as the time grows, the torsion gets smaller and smaller. The degree of twisting gets smaller and smaller. Basically, the curve has less and less twist. At the beginning, very much twist. The degree of twisting is very large, but then as time goes on, the degree of twisting slows down on that one. So yeah, know the formulas and how to calculate it. More questions? Yeah.
Could you just go over how to solve number 23 of 14.6?
Twenty-three, 26, 20,
23.
23. This one here. Okay. I think I understand the question. I think it's much like this, I think. So we can see it. Let me blow it up here. All right, what is this question asking? You get this temperature function, which is a function of x and y. The distance in the xy plane is measured in meters. You want to know how temperature is changing. You want to take a derivative of that. But x and y are also changing. The particle is moving clockwise around the circle of radius 1, around the unit circle. So both x and y are changing with time. And so this is like a related rates kind of question where I want to know how fast the temperature is changing with time. But temperature is changing based on how x and y is changing. And so I want to take the derivative of temperature, which will involve the chain rule. It will involve taking the partial derivative of temperature with respect to x and multiplying by dx dt. And then taking the partial derivative with respect to y and multiplying by dy dt. T is a function of x. I should be doing like this all the way. No delay. T is a function of x and y. It's x times the sine of twice y. If I want to know how t is changing, with time, lower t, I have to first find how t is changing with x and multiply by how x is changing with time. I add to that how t is changing with y, and I multiply that by how y is changing with time. Make sense? Make sense? Okay. We don't have either of those up. We have how z is changing with time. Like, basically, we know how fast the particle is moving at a constant rate of, oh wait, a particle is moving clockwise around, oh we know, what is that we know actually? Let's take a look at that. I have this unit circle, and I say how fast the particle is moving along the unit circle. Unit circle has the equation, x squared plus y squared equals 1. They tell me how fast it's moving along the circle. The particle is moving clockwise along the circle. The particle is moving clockwise along the circle at a constant rate of 2 meters every second. The circle's radius is 1 meter. In 1 second, I'm 2 meters along the circle. Anyway, how fast is the temperature experienced by the particle changing at the point when x is a half and y is √3/2. So that's the point on the unit circle right about here where x is a half and y is √3/2. What angle does that correspond to? Pi/3. Okay. So I need to incorporate theta somehow, or maybe z. What exactly is this 2 meters per second? We need to quantify that. We need to say this is equal to d something dt. Well, we can easily get this guy. The partial derivative of t with respect to x, the partial derivative of t with respect to y. Those aren't the issues. These guys are the issues. Y dt and dy dt and dx dt. Okay. Tangent, like a What is that 2? What is that 2? Yeah.
Like we'll need to take the directional derivative, partial derivative, and our vector will be log 2. Will be tangent to that to the when I make a line between the point and the circle and the arc, and that will be our vector. Yeah, I'll see the vector there. And
Oh, the different parts of it are dx dt and dy dt. Oh. So we have x and y as like our path, and dx and dy would be like the derivative of that. All right, I'm with you. That'd be like the velocity. What is 2 though? The speed? The magnitude of velocity? I believe that 2 is the speed, magnitude of velocity. And I believe that the position curve is, we're going to recast it so that we use theta. We're going to polarize it and say x is r cosine theta, y is r sine theta, with r being 1. I believe we have to, it's something that we don't normally do, but we have to parameterize this curve, cosine t, sine t, where t is like time, or theta. So that when we take the derivative, we get the velocity, and we want the magnitude of velocity to be 2. I do believe that's what they want. We definitely will do more of this later, like chapter 17, 16. Chapter 16, we do a lot of this. I have this curve. I need to parameterize it. I need to know what x is as a function of time, what y is as a function of time. It's nice here that it's a circle. But anyway, it's the velocity that we need. And so we take velocity to be negative sine t dt and cosine t dt. And particle is moving at a constant rate. So yeah, that's definitely dv dt. That's dv dt is 0. The rate is constant, meaning that its derivative is 0. This is the rate at which, I don't know if that's right. It should be equal to 1, right? Magnitude of velocity? Constant rate of 2. I really think we just plug in pi over 3 here. Velocity, it's moving at a constant rate. That means it's and that constant rate is 2. Is that right? Are we believing that or no? I don't know. I really think we just take the pi over 3 and plug it in. I don't know what this 2, how does this 2 play a role? What did it say in the answer to the back of the book for A? Maybe work backwards from that. Is there a way to skip to the back of the book? Nice. Was this 14 what? Take forever. Oh, here we go. Okay. Is this it? 14.4. Oh wait. Alright, that sounds good. No, I think. Number 20 what? Yeah. Yeah, we get that. Go back. Directional derivative, is that all it is? Am I overthinking this? Is it just a directional derivative? I don't know. I don't want to waste any more of your time. Might have to think about this and get back to you. That's really what it is. It's a dot product between, yeah. No, I think we're going to get this answer. But I could have posed it as a directional derivative, I think. What's the t partial with respect to x? Sine of twice y. What's the t partial with respect to y? 2x cosine 2y. What's the sine of pi over 3? Root 3 over 2? Yeah, I think we're going to get that answer. If I'm on a unit circle and I'm at that point, if I'm on a unit circle and I'm at this point here, the angle that I make with the positive x-axis is pi over 3. It's cosine and sine. You have to, you just got to know the unit circle to get that quickly. Yeah, I do believe we get that answer. What's y? Y is root 3 over 2. So sine of twice y would be sine of root 3. I got an extra negative here for some reason that I don't think they had, or maybe they had that. I don't know. This guy is a half, but here's a 2. And what's x? A half. And what's the cosine of cosine of root 3? I think we get that answer. I don't know. I think I got the same thing. I could be off. I think I'm off by a sign or something like that. I'm going the wrong direction. My thing isn't set up right. I'd be going counterclockwise in my direction. For me to go clockwise, I gotta flip the negative. I'm sorry, this is wrong. I gotta put my negative here, and yeah. For us to swing the other way, this, as t increases, we're going clockwise. No, I just flipped this guy. Don't flip the pi over 3. Leave the pi over 3 where it's at. But flip this guy. How do I make it go backwards? Put in a negative t for t. So this stays the same, but that goes flips a negative. Yeah, there's a negative here. I'm sorry. This is the problem about picking a random problem that I usually like to pre-assign them so that we don't. I think I put a negative here. I think then I go clockwise. Is that right? I could be wrong on it. Place t with minus t. Make time go backwards. That might be wrong. Anyway, but that's the point. You get close to it. Yeah. So in general, if you have a random question that you try from the book, shoot me an email about it. I need time to look at it. I don't. If I didn't assign it to you, generally it's for a reason. Some of the book problems are kind of way out there, and it wouldn't be something that I would ask. But stick to the final exam questions, the My Math Lab. Maybe then at that point you go try some book problems, but I gotta be careful when you pick them, I guess. I think this is a directional derivatives question. I didn't pose it like that, but pretty much it is. This guy here is my gradient dotted with the unit vector. It really is a directional derivative, but I just didn't pose it like that. I don't know. Sorry. Yeah.
So what's the last section?
So our page is now updated with that information. $15.1. Yeah.
Well, 15.1. Could you explain why we use the right-hand points of the rectangle?
You can use whatever you want. They told you to.
Okay, so could you
You can evaluate the function anywhere. You were dictated though in that problem to evaluate them at the upper right hand corner. There's a star here, meaning that it could be anywhere. It could be the center, it could be the corners, it could be the midpoints, it could be anywhere. But you need to go get the height of the function someplace on the rectangle, and so there's some point that you'll have to plug in every time to the function. In this particular one, it dictated to you that was the upper right-hand corner. It's no mystery. You have to be told where to go evaluate the function at. The xi star, yi star, yj star needs to be told to you. The change in A is the area of the rectangle. So the area of each rectangle here should be the same by the way it's split up. Delta A should be the same. It's delta x times delta y, and you'll get the change in x times the change in y. You'll be able to figure out what delta A is, because these will always be rectangles. Yeah. Yeah.
And then for when we're integrating over the rectangular region, volume, it doesn't matter which order we do it. Okay?
When they're rectangular, it doesn't matter which order you do it in. So that whole argument about what comes first is out the water. That doesn't come into play until 15.2 and 3. Yeah.
Will we need to know how to do the estimation of the?
Yeah, like this question.
Yeah, we're gonna have to know that.
You might have to churn out one of those, yeah.
Okay.
Yeah. Plug and chug, work that out. But I'll be definitely sure to ask one where you have to actually do the integral. Give me an exact value, not an estimate. Yeah.
I think I have an example of one of those problems on one of the Torsion past exams.
Oh, you got that? Where's you?
I have it here in writing. I'll show you that.
Say it again.
I have it here printed out.
Oh, you don't know where it's at online? Okay.
I can email it to you.
Okay. This is from the Turk.
It's the second victim.
This is a linear approximation question, a differential question, a use the tangent plane to approximate question. I have this function, and it says the linear approximation, that's a code word for tangent plane. The linear approximation is the tangent plane. We use the abbreviation L for it. It's the x partial times x minus x, not the y partial times y minus y, not, I think there's something else though. Let's go to the notes on that. I'm sorry. Off the top of my head, I can spit it back out. These are notes from section 14.6. Yeah, okay. Plus the function value f of a, f of x, plus the function. The problem with this guy is that it's z in there. It's not z is some f of x, y. We don't have that. Z is mixed in with the x, y. So we can scrap this really and go with the capital F, where we take, basically, we find the tangent plane by taking the x partial, the y partial, and the z partial, plugging in the point of interest, x naught, y naught, z naught, multiplying by the associated part, x minus x naught, y minus y naught. So we need to find the equation of the tangent plane, basically, bottom line. So this is a way to do it. It'll be equal to 0. So we go get this capital F function, which is already there really. Maybe set it equal to 0. Zx plus e to the xy minus 2 is this capital F function. What's the x partial? Z plus y e to the xy. What about the y partial? And the z partial. So then we evaluate these guys at the point of interest. X is 1, y is 0, and z is 1. Since y is 0, that kills this whole exponential term. Here, though, we get 1 times e to the 0, so we get a 1 there. And then we get a 1 here. All right, great. And so those are like the A, B, and C. We take 1 and multiply it by x minus 1. We take 1 and multiply it by y minus 0. We take 1 and multiply it by z minus 1. So that's our tangent plane equation. It's x minus 1 plus y plus z minus 1 equals to 0. X plus y plus z minus 2 is 0. That's the tangent plane. Now, we shouldn't have done it like that, though. We should have left it like this. Let me show you why. Okay. I need to try to evaluate at this nearby point. Okay. I'm at 1, 0, 1. I'm going to change x and y by some small amount. Okay. I'm going to change x by going down by 0.04. I'm going to change y by going up by 0.02. In the same, I'm going to change z as well. I guess I have to go and get what z is at that point, or not. It won't matter, I think. So the point is that instead of this version of the tangent plane, I should go with this version of the tangent plane. Because what I'm doing is I'm going to plug into, it's a linear approximation, tag word for tangent plane, and I want to estimate the value of z for this point. Okay, and so the value, according to this equation, the value of z is x plus y minus 2, apparently, I guess. If I plug this in, x plus y minus x plus y x plus y plus 2 2 minus, geez, what am I saying here? 2 z equals 2 minus x minus y. That's my tangent plane equation. 2 minus x minus y. That's what z is. I have an x, I have a y. I'm just going to plug right into here. I could have used this as well, though. That would have worked too. Either way, I think this works so much better now that I look at it. If x is that and y is that, then I'm going to get 2, take away 0.98, which is 1.02, letter F. Okay. There probably is a more elegant way to do that, but I think that, so you have to do code word transformation. Linear approximation, tangent plane. Go get the tangent plane equation. Either one of these guys will work. I'm thinking that this one works better, though. And so we're trying to get an estimate for the value of z. So let me take and solve it for z. And apparently, by using the tangent plane, if I take 2 and subtract the x and subtract the y, I'll get what the z is. And so, at that point, corresponding to this change in x and this change in y. So I could have done it a different way. I could have done it, he said it here, using differentials. I could have done it that way too. But I did it using the tangent plane, which is the same thing, essentially. Yeah. Yeah. So I saw a linear approximation. I immediately went for tangent plane, but I could have done his parenthetical comment. I could have done differentials and answer the same question, the same kind of way. I want the change in z. By changing x and changing y, it forces a change on z. My goal is to figure out what the new z is, and differentials would have got me the change on z, and I could just subtract it from the original z. I could have gotten it that way too, but the answer definitely is 1.02. This is a good question. It's good. It's good. Another source of problems. Yeah, he has tons of problems. He taught the class that year with me not last academic year, but the academic year before that, and he gave some good problems. That was one of them there. Yeah. So as a third source of problems, first there's our old finals, and then there's our online. This is a great source. All I did was just Google Deterk Math 114. I immediately came to his Math 114 page, and he has old midterms there. He has old final exams there. He has a large source of problems. He has a lot of practice problems, and yeah, these are all legitimate questions that we should know how to do for the most part. There might be a couple that we don't do because we changed the syllabus since then. Yeah. More questions, please. So on Monday, we'll take the exam. Between now and Monday, I'm around Monday before class. I'm around Thursday, pretty much until 2:30. Friday, a little sketchy. I'm not around as much. But there's plenty of ways for you to get help between now and then. Emailing me a question is a good way. There's these help sessions that you can go to. I recommend going to the Sunday night review. In A4, there's someone there to help from 7 to 9 p.m. In the dorms from the hours of 6:30 to 9:30. So I guess tomorrow will be the only time. It's in Ware College House. There's somebody here waiting to answer questions. There's always someone in Education Commons is this place in the football stadium above Breezy, in between Breezy and the workout room. There's this new place where people study at. It's from the library. It's called Education Commons, and there's someone there just waiting to answer questions. It's just drop-in help. The person there is able to just from 4 to 7 p.m. just waiting there to answer questions. You need your ID to get in, but everything, yeah, that works out nice. And then Sunday is in DRL. Well, yeah, use these. They are underutilized, and so and then there's late night help. I don't know if anyone ever used this, but there's a discussion board. On your Blackboard site, there's our lecture site. There's no recitation for this class, but you should have access, if I'm not mistaken. You should have access to the plenary site, and so you should be able to post a question during the hours of 9 to 1 in the morning to this discussion board, and someone should be there to answer that question. Actually, these people here are really good. These people here in this, these are a couple of our best people here that are answering these questions. I don't know this person here, but yeah. So anyway, more questions, please. Yeah. Will I answer questions before the exam on Monday? How did we do it last night? I just said, ask me questions, then we ran out and we just took it. Yeah, I can do that. I'll be in office hours an hour before class. That would be the best place. I'll be in my office an hour before class to answer questions. I'm really there actually from 4 to 6, but usually at 4 I have a student in or something like that. But if you can't do 5 to 6, I can do 4 to 5. But that's the best time to get help. And then yeah, I can start off with the same kind of question and answer session. Once we run out, then we'll just take the exam. Yeah, I don't know. Check this. I might be lying, but I think the night students should also have access to this. I don't know. Somebody double check me on that. When you go to Blackboard, you should see 2 Math 114 sites. More questions? Had enough for tonight? All right. Have a good weekend. I'll see you guys on Monday then. Yes, sir. I was wondering
why my math even the one that we went over in class and we didn't finish it up, the one where like we're trying to, it's like negative 3/4 times AB, and you have a plus a squared plus b squared, and then you have AB equals 0. So the I found out what A was and B was, and I tried typing it in, but apparently that's not the answer. A is 3/5 and B is 4/5. No, sir. Yeah, it's one or the other.
Is this right?
Um,
Everything we have is right?
Yeah.
Okay, so A is 4/3 of B. Take that into here. So 16 ninths plus 9 ninths, 25 ninths. B squared is
Just into 3/5.
is plus or minus. So when B is 3/5, A
It's 4/5.
4/5. When B is negative 3/5, A is negative 4/5. There's two values there, and so we get 4/5, 3/5, but we also get negative 4/5, negative 3/5. When I dot this with this guy, I should still get 0. Negative 12/5 plus 12/5 is 0. Not here though. Oh no, positive 12/5, negative 12/5 is 0. Okay, that works. So I get both of these used. Which one do I use? Which one do I use? They both give me a dot product of 0.
Well, they're saying that that's not the answer.
Okay.
Like,
So you put it in.
Yeah, I put it in with 4/5, 3/5, but regardless.
No, you didn't do it as a vector.
How do I just put I then?
Simplify your answer. Use comma to separate answers as needed. There's two answers, and type your answer in terms of I and J. You just didn't follow protocol there. That's all.
Notation.
So I and J.
Do I need parentheses?
I would use plus. If you're going to talk about I and J, you got to use plus. So 4/5 I. This is 4/5 I plus 3/5 J.
Okay.
That's what they want. And then the other answer is negative 4/5 I minus 3/5 J. That's all. You did it right. You just didn't give them what they want in the form they wanted. I hate that you have to go through that.
You still get it wrong.
No, you can't just put I and J as letters. You got to use I as a vector. You got to go to the bold I.
gotta go to the
You got to
bold
go to more.
Okay.
Like you got to. Yeah.
Okay. That's great.
Oh man, it's already due. It's due Monday, and we can have Monday. So yeah, I guess tonight. You can't give me an extra day. That's not fair. That's an extra night. I can't do that. It's not fair. So I'm saying you can run home and come back and give it to me. I'll accept it. I'll be here. Okay? I can make a copy and give it back to you. Yeah. I'll run it. Call me upstairs. So, yeah.
Oh, because you need to type in both. So you need to type in 4/5 I and J and then a comma after the J and negative 4/5 I.
So where are you from? I'm from LA. Where? LA. LA? Oh, that's cool. I'm from LA. Cool. It's been like 40 minutes away. Really cool. You miss LA weather? Yeah, it's usually one of my really good friends goes to Princeton. He goes to USC. Oh, cool. And they're like, loving. They went to the beach last week. What the hell? Yeah. Okay, cool. It is.
It looks like it is.
That's good.
If you have more trouble, I can by email talk about it.
Hi, I
Hey.
just wanted to confirm for the online homework, since
Mhm.
15, 2, and 3 aren't going to be on the exam, do we still have
I
to
never
do that?
put them on the homework. I
Oh, they're
never
not on
even
the
did
homework.
them. There's not even 15-1
Okay.
up. I said it on the web page, but
Right.
then I never even made the
Okay.
questions
So
for
it's
them.
not due on Monday?
So none of that is due on Monday because it's not even up yet.
Gotcha, so we just, whatever's
But
on there.
1458 is up there, so that
Okay.
should be due.
Cool.
And that makes sense because that's what's on the test.
Right.
That's okay?
And did you get my email about the show?
Yeah, the show.
Okay.
Yeah, so put me down for, what day of the week is it?
Friday or Saturday?
Okay, not this weekend, but next weekend.
Yes.
All right, so put me down for 3 tickets.
3 tickets on. If you don't know right now, you can just reply to the email before Sunday, but
Okay.
it's up to you.
Yeah, 3 tickets, let's say Friday.
Friday? Okay.
3 tickets Friday.
Cool. Sounds
I
good.
might need another ticket.
All right. If you need another one, just email me.
Yeah. All right, sounds good. Thanks. Okay.
I was just wondering, like, what the if the format of the exam is just like
Same.
multiple choice, and then is that like,
Some are open-ended maybe, I don't know, but most part multiple
like
choice.
even if you miss
They weren't all
multiple
multiple.
choice, if you miss the question, the answer, do you lose all the points? Or
Wait.
is it like graded?
It's graded for partial credit.
Oh, it is. Okay.
No, I think
Yeah.
I just want to chat. I just
I'm
want
sorry, 1 second.
to see the chat.
Hello? Hey, you found your purse? Was it in your backpack or was it in the green bag?
Where's the bag?
Oh, it's in the book bag. Oh, good.
There.
Okay.
See, like, I just did the check method. You know, I did the wrong way. I think I thought one of the x equals so it doesn't exist. It'll just be infinity, right?
When you get positive thing, when you get negative thing, you say you don't need to.
Should I change it? Yeah, I don't know.
What this does that?
No, just ask him. Wait, what's wrong? No,
It just doesn't exist.
Oh, you just put infinity.
Yeah.
Oh, you looking it up? Okay.
Yeah.
So that's what you want? For your birthday? Just randomly, you just thought you called me and told me? Okay. We'll work on it. We'll see. Alright. Alright, talk to you later. Okay. Wait, did you go trick or treating? Did you dress up? You got your costume on? Did you go outside and go trick or treating? Or no?
Could
No, that's okay. You got your costume on, though, right? Oh, nobody came to your house to trick or treat? Did you give us some candy? Tell them to go away? Did you answer the door? Oh, okay, no trick or treating then. Okay. Did you go out here? All right. Okay, lovely. Your birthday. iPad mini for the birthday. Got it. iPad mini for the birthday. I got it. Okay. Okay. Bye. 5 minutes.
She's 5.
Randomly. Yeah, I'm rocking that. I'm sorry. Who was next? Oh, yeah. Mm-hmm. No. No.
Go for it.
we had
I had 2 different things. On the homework, so I screwed it up royally for the limit question. So like I had forgot my methods of, like, for the first one I did my methods of checking.
And they all agreed?
Yeah, but I did it wrong. I did these 3 and then I forgot the other one, so I just did x equals y, which was the same.
Yeah.
Okay.
If they all agreed, then chances are some algebra that you can do to
Okay.
fix it up. So,
Okay, and then like for this one, like apparently I wasn't thinking, so when I left like 1 over x, I was like, oh, the limit doesn't exist, even though it would be
It's infinite.
infinity.
Yeah, it's different.
So yeah, should I just like leave it like that, or should I actually?
I mean, it's.
I feel like cheap if I like change it now, but yeah, because I realized like as we were going over, I was like, oh, crap.
Leave it like that. I mean, he should give me something partial for it or something.
Okay, cool.
Now, he doesn't even grade them all. He just grades a couple of them.
Okay.
He grades it partially on that you tried, and then partially on, he picks a couple of them and go and actually grade. So,
Okay.
yeah.
So it doesn't like we just have to show 2, right? Like plus minus.
2 pass.
Right.
2 passes are enough.
And then so I had a question on this one. Like I've been struggling with this slide forever.
Really?
Yeah. It's
Why is
just,
that?
I don't know. I
think it's
can't
really
think about it. Like, how do I know that like
for example, like 55, right?
Yeah.
How do I know it's f? Like,
As x and y go to 0, that denominator is going to 0.
right.
Small denominator means the whole thing is
So flat.
very big.
Right.
Other way around. Very big. At the origin, this thing blows up.
Right.
1 over something very small is very, very large. Only one of these functions blow up at the origin. F. Blow up as in give me a really big z value. But the other way around. X and y get big.
That's what I was saying. That's the way
Then
I was trying to do.
flat.
Then it flattens.
Any of these that flatten out, just
C,
one of
I
these
did
two.
C and F, so I didn't.
Yeah, so
I
they
was
were down
like,
to
which
that.
one?
And then we process elimination that one of the other guys should go with. You see, why should there be these peaks in each quadrant? Like what? You know,
Right.
This one has that kind of symmetry to it that there should be peaks in each quadrant. So,
How do you-
so yes, things like that. You know,
How do you know there are the peaks in the quadrants? 'Cause it's
you don't know by looking at it. You got to do the analysis to figure it out. But
Okay.
there should be some symmetry. This one has some symmetry that this one doesn't have. This graph definitely has major symmetry that this one doesn't have.
Right.
When
And
you
if you
flip,
plug in 0, you get 0 here. So that'll tell
okay,
you.
that's another reason why this
Right,
one's
that
0
that
at the
one-
origin, while this one blows up at the origin.
Right.
So that can define it. So it's a process of elimination, but all
I
these things.
see. Fantastic.
Yeah.
Okay.
Okay.
All right.
Alright.
Sweet.
Yeah.
Did
Did that work out? What was
Yeah,
that?
it worked out. It was just like
They had a both eye or something you could push?
No, you couldn't, but like you had to put both answers.
Oh,
Like
okay.
just
But
one.
just pushing I was fine.
Yeah,
The
pushing I
the
was
letter
fine.
I.
Yeah. Yeah, it's
Okay. And they wanted both answers separated by commas.
Yeah.
Oh.
I'm sorry.
I was wondering, I had a question with the notation.
Oh, this is what we're doing. That's what I was doing today. I said.
Yeah,
uh-huh.
like, I understand the concepts and everything,
Okay.
but then like, you use partial D's here all throughout.
Because z is multivariable, but x and y are also multivariable. Over here, x and y are single variables. So I took the advantage and only use a d for when it's single variable,
Oh,
and
I see.
and a delta when it's multivariable.
Okay, but like, presumably, the x's cancel out.
Technically, yeah, that's what you think about.
And the y
it.
cancels out.
Kinda, yeah.
So then why wouldn't the answer be like partial D?
What do you think?
Like, why wouldn't it be a curved D?
Because t is a single variable. I basically I could recast if I wanted to. I could recast this function and have all t's in it because x is a function of t and y. I can plug in. Everybody can see
Okay,
x
yeah,
for g.
yeah. Alright.
So really is I could say that z is a single variable function of t. That's why I have a single variable derivative d.
Oh, I see.
Yeah.
So like, in most cases, we'll be using this.
Almost everything.
So like all
Everything's
all
partial.
is partial. Okay,
Yeah.
alright, cool.
Yeah. Uh-huh.
So I kind of have a really good
Yeah.
no,
Okay.
it's fine.
Fine with me?
I have a work link and I kind of really should.
Okay. So you make it up.
That's okay?
We'll figure it out.
Yeah.
It's you know.
I just want to get these.
It's what we have to do.
Okay.
Okay, so we'll find some time. It has to be after that. We make us before.
Okay.
So what is it? That's a Wednesday, the 12th.
Yeah.
So we'll try for sometime Thursday or Friday.
Anytime would be fine.
Okay.
Whatever. You just let me
Figure it
know.
out. I don't know when I'm around, but we'll figure it out.
Okay.
Okay?
Cool.
Yeah, I want you to, if you have to be there, you have to be there. And this is stuff we have to do for math class. I have to make them problems and do things.
I know. If I didn't have to be there if you wanted me, but like that's kind of what I just wanted to do the whole year.
Oh, you gotta go. What's it? Is this a culmination of something?
Pretty much.
Oh, you gotta go. It's okay. We'll work it out.
Thank you.
I'll work with you.
Cool.
Okay,
Thank you.
Lisa. All right, yeah. What's going on?
I don't see the sign.
There's lots of symmetry going on here. And the sign.
Yeah, so I know like when it's
Oh,
like,
periodicity, first of all.
right, and then like no one's a trig, you know, there's like has that period going to it.
57, 58, 53, periodicity. Right. This one though is different than these two. Another thing that's on the list of things to think about is if you replace z with a constant, then that's going to tell you what these curves should look like. That's slicing your surface and getting the curve that's on the plane that you slice with. If I say z equals 1, okay, if I slice at a height, z equals 1, I'm going to get a circle. I'm going to get, why is that a circle? I know it says sine, right? Sine of something. But really that's, what is that? X plus y squared is, so what is it? What is that? X squared, thing, I don't know. Why is that is your question? And not, what are the other options? Yeah, this is periodic in both x and y.
So that's how you know it's 57. I mean,
Periodic in both x and y. Like there's no difference between x and y. Same thing here. There's still no difference between x and y, but this is periodic, but periodic with parabolas. Periodic with parabolas.
Oh, okay.
You know what I mean? So that makes the periodicity stand out here. But still, why this and this then? Why this circles? Why these concentric circles centered at the origin? Why is that? And it's basically that if I say the sign doesn't play a role, I think the sign doesn't. If z is 1, what does that say? 1 is equal to the sine of the square root of x squared plus y squared. What is that really saying? That should be a circle apparently. Why? It's constant on circles. What does that mean? Any point that has x squared plus y squared equals r squared. Any point that's on the circle will give the same z value. Let's say that instead. That's a better way to say it. Any point that is on the circle of radius r, you'll take this x squared plus y squared, and you take a square root. What you'll get out is an r. And so any point that's on this circle of radius r will have the same z value. Z will be the sine of r for all those guys. That's the key. So for all the guys on a circle centered at the origin, they'll have the same z value. So that's all the guys will have the same z value. If I pick z equals 1, I have everybody on that circle will be that same z. But if I pick a different r, everybody on that circle will have the same z. It'll be a level curve with concentric circles emanating out from the center, and all the points on that circle will have the same z value. That's the level curve part of it. So you should have these kind of ripple effect that this thing is having as it continues on. Like we only see part of it. There's like this continuation of rings here.
Yeah, it shows it on the.
It's definitely 3.
3.
B and 3.
So if we see like an x squared plus y squared,
You should think circular.
always think
100% think circular if you see x squared plus y squared.
So why is it? So on here it's just like, even though it is circular, it's just kind of like it just goes to
Elliptical. Because the coefficient on y squared is different than the coefficient on x squared.
Oh, right. Okay, so that's why it's like kind of like that. It looks like an obelisk almost in the middle.
And that's why these guys
like
are
ortho.
ellipses
Okay,
and not circles.
I see.
But
I see.
Had they been the
Why is
same,
it creating-
had this
why
been
is it-
4x squared and 4y squared,
Yeah.
these guys would be circles.
Okay.
but why is it creating circles at all? Is my for this one?
For that one,
Yeah, why is it creating? Ellipses at all?
if z is say z is some constant.
Yeah.
So k is 1 over x squared plus 4y squared.
Yeah.
Multiply, you'll get kx squared plus 4y squared equals to 1. And so x squared plus 4y squared is, or maybe put these over k, I don't know. Maybe even this is anyway, the point is,
It'll come out to an ellipse.
you know what I'm saying? Ellipse,
Okay.
come
Yeah,
out. Ellipses come out of that.
yeah. Okay.
Yeah. So the level curve should be elliptical, and that's the only one that fits that.
All right.
It's those type of things that you think about.
No, yeah.
Yeah. I'm sorry. You ready?
Yeah.
Did
No,
that answer all your questions that you had by email? Or no?
urgent. No, well, it was fine.
We didn't get them all?
No, yeah,
You did?
no,
You did
we
get
did
it?
it, yeah.
Okay, that's the point. I'm sorry. I couldn't answer them by
I like
email.
always freak out and then I can work my way through most of them.
Oh, good. That's a good thing, you know. That shows. I know you're working hard. I can tell. Yeah, good stuff. All right, so wow, 39 unread emails. That's kind of scary. Jeez, I'll never get them all answered.
One might be that you can but I'm not
Since the last time? Since
Yeah, I asked like how far the test was gonna go.
Oh, you okay now? You got it? Okay.
It was like
That was in class? You emailed me or before class?
no before. This weekend I think.
Or I think I saw it. Yeah. Okay. All right. So we're off to make copies.
Can I ask a real quick question? On the points dropped from the homework, Does that include online and in class? Like is it a combination of both?
We'll drop some percentage of the online. We'll drop some percentage of the hand-in. Some small, like 5% or something like that.
When do we see like our grades on?
I just got a grader since the class enlarged on me. I can't keep up, so I got a grader, and he told me he's done with your first 2 assignments.
Okay.
And I'll give this to him. He'll have a quick turnaround because his only job is to grade for us. So he'll have a quick turnaround on these. And I just need to make him a part of our class on Blackboard, and then he'll start throwing these up on Blackboard. That's all.
Oh,
So it should be.
Did you get my first homework? Did I email it to you?
Oh, I didn't. I will. Thanks for reminding me. Email homework. I gotta look for that.
Alright. See you, Professor.
Okay, take care. See you. Yeah.